Okay, good afternoon, everybody. I hope everyone's having a wonderful day. So before I get started, just a couple of things, just as reminders. Remember, reading week is next week, so we don't have classes next week. But I must stress that I do have my office hours still next week at their scheduled time. So you're more than welcome to still come by my office hours next week. I will be there. So I like to make sure I'm available to answer any questions, especially given the other announcement is that the upcoming midterm is coming up. It's technically next class that it's scheduled on. As I mentioned, I was mentioning just a moment before, this is all being done within a Your Courses quiz on the website. So this is, again, like I said, it's been done through ProctorTrack. So make sure if you haven't done the onboarding process, make sure you do that. Unless I've talked to you specifically. The other thing that I want to remind you of is that I'm going to be putting out the format for this test on Monday or Tuesday, okay? That's at least the plan. Also, do keep in mind that the assignment 2 deadline is creeping up very, very soon. So make sure you submit your assignment within the time appropriately. Assignment 3 will be coming out either tomorrow or on Saturday, okay? So the third assignment is I would argue is probably one of the shortest assignments of this term. So just don't let that dissuade you from completing it as early as you can. You'll have everything to start working on it. And also you could just finish it just in one sitting, even if you are, I don't know, determined enough. You probably could pull it off in one sitting. But just be warned, it's like any other programming assignment. You have to take that time and make sure it's working properly. I usually am very detailed with my specifications for programming assignments, so just make sure you read them very carefully. Okay, keep in mind that won't be due for a while. It won't be due until about March 9th. So by the end of March 9th with the 8:30 rule in effect. So you have quite a while until then, but it will creep up. So anyways, before we get started, are there any other questions before we kind of just jump into things? Because I got an interesting topic to talk about with you today. Okay, I think we're good to start. Let's talk about what we're going to refer to as splay trees. Now, before I do that, I just need to give us a little bit of a reminder, is I need to talk briefly about binary search trees. So recall BSTs. So here's one definition for a binary search tree. This is the one I'm going to use. You may have seen a variant of this definition. I'll clarify on that in a moment. So I'm referring to a binary search tree as a proper binary tree. Now, if you're not familiar with what a proper binary tree is, it's a tree where every internal node has exactly 2 children. So this is in contrast to a binary tree, which can have at most 2 children as opposed to exactly 2 children. So this is an additional constraint I'm adding in, but keep in mind that this is an equivalent way of defining a binary search tree if you've seen it the other way around. I'll explain in a moment. So the proper binary tree is going to store records. So I'm going to make the presumption of a dictionary-based implementation where I'm going to have unique keys so that when I make comparisons, no 2 keys are going to have the same value. But keep in mind, like I said, you can define binary search trees where the keys can have it where there's equal values in the trees. They're duplicate values for the keys. In its internal nodes, where each internal node U satisfies the binary search tree property. So you've probably seen this one before. If I examine any one node U that's an internal node, it has to be that if I look at its key K, it has to be that all of the left subtree, so if I look at its immediate child to the left, this subtree consists entirely of nodes where every key is less than my key, less than K. All the keys in the right subtree, which is rooted at the right child, all of those keys have to be bigger. So you might be familiar with this definition of a binary search tree, right? There's just a couple things I want to clarify because I asked you just to take a quick peek and just to remind yourself of binary search trees, but I know that some people see different versions of or ways to implement binary search trees. So I just want to make a couple of remarks just because I like to see where everybody is at. So for some of you, you may have heard of binary search trees where, for example, what I've described right here, you may call that a binary search tree, but not necessarily by this definition, where each one of these, say, has a record in it. You may have been given a definition, and it's okay definition. It's equivalent to this one in a different way. This one, you would have every one of these having a record in it. But notice it has at most 2 children for each internal node, where these would be the leaf nodes of that tree. So first, I'm sure some of you have seen this definition. Can you like give me a thumbs up if you've seen that before? Yeah, it's a pretty common way of representing a binary search tree. So what I'm saying in this definition is that I'm going to have it where the records are all stored in internal nodes, like this, except I'm going to have leaf nodes that I'm going to introduce. So these boxes here all are nodes, but they have no data in them. So these they won't have any data in them. They're just going to be a node. They're just a dummy or placeholder node. But these leaf nodes, they don't have data in them. But now notice that my binary search tree, all of the internal nodes have records in them, and it has exactly 2 children. Does everybody see that? So this is one way you can get the exact definition I just gave right here. Does everybody see that, just to be clear? So this is actually one other way you can implement a binary search tree. So each one has their own pros and cons. For example, the way that you may have seen where you have at most 2 children, regardless if it's an internal node or not, is that you have to deal with null pointers very often, right? You have to be careful not to go too far down, or you don't want to assign something to be null that isn't null, right? I like to think of this implementation like, or this representation based on this definition, like binary search trees with training wheels. So what happens is, notice that if ever I want to do manipulations or insertions or removals on the tree, all I have to do is follow down the tree until I hit a leaf. I never have to examine if it's null or not. It's either I hit a leaf or I hit an internal node when I'm doing searches, for example. There's one advantage to this representation that I'm not going to say too much about because it's more of something I talk about with AVL trees, is that this implementation has the advantage that it makes it very easy to perform rotations, or at least implement them. For example, you could take any one of these nodes, any node in this tree you could take as an anchor to perform a rotation, such as in an AVL tree. So it makes things a little bit easier to play around with. You never have to play around with null pointers, which is a really nice feature of this one. The con, of course, is that we take up at least one extra level of space with our nodes that don't store anything, right? So the way you've seen it in class, that's an optimized version of this one. So are there any questions about that? So the one that you may have seen before without all these placeholder nodes, that one's actually an optimized version of this one. So anything I say about the algorithms today, or anything I say about binary search trees, you can easily translate between the 2 representations. You just get rid of all these dummy nodes, or placeholder nodes, the leaf nodes I have here. And you just replace those with checks on null, right? So anyways, what we're going to be interested in terms of operations for our binary search trees are so-called dictionary-based operations. So 3 question that we're going to focus on are get, which is the equivalent of finding. So if I give you a key, I want to see if I can find it in the tree. And it'll, of course, give me back where that is. Put, that's where I want to do an insertion of a record into the tree where it has a key and it has a value. So that's how dictionary data is always stored. It's as a record, and the record has a key, which is always unique in the tree. And it has a value. So this can be any kind of data that you could think of. And then lastly, remove. This is just your removal from a binary search tree, where I just give you a key. Your job is to delete the one that has that key. So are there any questions about binary search trees? This is just a reminder, but also I just want to bring up just one convention about binary search trees that's going to be relevant for us and how I present this today. But yeah, just to keep it simple, if you ever think about anything I'm just saying here, you could just ignore these boxes here and you would have another way of thinking about the binary search tree. But either one is perfectly valid. You can implement it either way. Just each has their own pros and cons. But yeah, so if we're okay, so first, are we okay with this? Give me 2 thumbs up if we're okay so far. Okay, wonderful, wonderful, wonderful. Okay, so now I want to start moving on to talking specifically about splay trees. Now you've probably seen several or at least one kind of binary search tree. You've probably seen at least the vanilla one where you can do insertions and you can lead to all sorts of nasty cases where, for example, in the most extreme case, you can have it where you perform a whole series of insertions where the binary search tree degenerates into a chain of nodes that go all the way to the right or all the way to the left or may even zigzag like this, causing linear running times for our binary search trees, right? Because all of these binary search tree operations, all of them, they take big O of h, or big theta h, in the worst case, where h is the height. So the natural question is, okay, so how do we deal with that? So in 210, you may have seen, how many of you have never seen an AVL tree before? Like, I'm not expecting you to be pros at it, but have you ever heard or seen of one? Actually, how many of you have seen one and how many of you haven't seen one? So I like to just kind of get a flavor for this. Yeah, I see that's kind of, yeah, that's what I would expect. Yeah, so some things I'm going to talk about are going to be reminiscent of the discussion of AVL trees, but I'm going to start as if you don't know much about it, regardless. So some ideas, they're going to sound very familiar to if you've seen AVL trees before. And that's a feature of the splay tree. So you may have heard of so-called self-balancing trees, such as AVL trees. There's other ones, such as red-black trees. What you do with those is we try to rebalance the tree so that the height is always logarithmic. So what we do is we perform so-called rotations to fix the tree every time we mutate it. So for example, if I do an insertion, I perform some rotations to rebalance the tree. Almost like, imagine if I had this hanger here. I imagine I had a thread that runs across here, and I imagine how many nodes could be sitting on one side of the tree to making a very, very, very high depth down this way versus down this way where maybe it's not as deep. It could be the case that one's a little bit off balance from the other, leading to where one side is degenerating more than the other. So the solution with an AVL tree is you enforce a property on all the nodes, akin to the binary search tree property, but you maintain the heights so that the heights are no different than 1. This is the so-called height balance property. So that's what you do in an AVL tree, is you enforce this property and you use this idea of a rotation to rebalance the tree by effectively pulling the string along the top of this, to pull up that part by taking off some of these weights and putting them over here. So these are so-called rotations, and a lot of self-balancing trees do this. But here's the thing, there's sort of a catch about this, is that those rotations, even though they're not too hard to come up with, you do end up getting nice running times. For example, logarithmic searches, insertions, and removals. But the structure is very rigid, as in you have to obey it at every node, meaning you might perform several mutations to this tree when you have to do all these rotations. In practice, they could lead to things being a little bit more complicated than you initially anticipated, even though they have nice worst-case time complexities. So red-black trees, AVL trees, that's mostly what I'm referring to. They have much more of a rigid structure to them about how we balance the trees. Now, what I want to show you is what we're going to call, some people in the more data structure side of theoretical computer science would often refer to as sort of the black magic data structure. So like this is one of the examples where amortized analysis gives you a very, very strange insight into how something, where it isn't necessarily as rigid as an AVL tree or a red-black tree, in terms of what it needs to perform, can lead to generally well performance in terms of time complexity in the whole. So what I'm going to do is, instead of thinking about, okay, every time I mutate the tree, I'm going to maintain this rigid structure everywhere along the tree. So very often in those algorithms, I work my way up the tree and I perform these rebalancing operations. Now, here's the solution I'm going to do. Instead, I'm going to be lazy. So I'm going to be lazy about this. So that's what I'm going to be doing, is I'm going to, instead of being very strict about where all of these nodes maintain a property, I'm going to be lazy. That says lazy, by the way. It subsumed the splay. Almost like it's sitting on a lounger, splaying the legs just wide apart like this. Just lounging back. That's my approach for rebalancing the tree with the splay tree. So just keep in mind that it's not going to be nearly as best way I could describe it is that a lot of the data structures that we've seen and some of the algorithms we've seen all are based on the idea of an invariant, where what I do is I have a data structure, it satisfies a property. For example, we talked about heaps. So before I apply an operation to my heap, it's a heap, right? So usually the goal is I perform some operation and it has to stay a heap afterwards, right? That's how AVL trees and a lot of these self-balancing trees operate. Now, splay trees are not like this. That's the first thing I really want to point out to you, is that it's actually one of the oddballs. It's like black magic. You're going to see that it's going to come up with a very fascinating result, even though it's going to be very lazy with how it attempts to adjust the tree for balancing, but it's not going to be as strict, and it's not going to guarantee that it's going to balance the tree. But the point is that I'm going to be lazy about it, and we're going to see what happens, okay? Does everybody understand the idea here? Is that on one side, you have these really robust guarantees on the running times, but very often they're based on invariance, and maintaining these could be potentially expensive and maybe a little bit more difficult to implement, versus something that's a little bit more lax. It may not have the same guarantees as, say, like an AVL tree does, but I would like the operations to be easy to perform and super easy to implement. So you see, it's kind of like a continuum here. So I'm going to show you through the kind of an introduction to these splay trees that have this nice property to them. It's going to be like black magic. You're going to see how this is going to be. You're going to ask yourself, why the heck is this doing what I think it does? So that's the big idea here. So that's why I really want to show it to you. And this is going to be like the last of the main data structures I'm going to show you, just because of that fact. Is it brings together amortized analysis and it breaks the mold of everything I've shown you up to this point. So is everybody okay with that? Does that sound interesting? Okay, so anyways, we're going to take two ideas and bring them together. So first, I'm going to use the rebalancing operations you may have seen with something like an AVL tree. So for example, if you're not familiar with these are the same, I'm talking about when you have like an AVL tree or a red-black tree, there's this idea of a rotation of the tree. And it's based on what I did with this hanger a moment ago. So suppose I want to readjust the tree by promoting and demoting nodes. So imagine I have a tree that looks like this, where T1, T2, and T3, these are all subtrees. And I have X being the root of a tree, where the left subtree is T1 and the right subtree is T2, and the right subtree of Y, the parent of X, is T3. So if ever I wanted to promote X to try to adjust the tree, similar to what I described with my thread, to try to push the weight around to readjust my tree to attempt to rebalance it, this is what the rotations are going to be about. So here's the idea. There's this operation we call rotate. I give you a node, and its job is to promote this node and then demote its parent. So what do I mean by this? If I give you X here, if I rotate on X, it promotes X, and then it demotes its parent. So X becomes now the parent of Y, and notice that there's something interesting that goes on in here. Notice that this one subtree here, this T2, becomes now the left subtree of Y. It kind of gets trade it over, kind of like what I was saying with the string, where I pull the weight off one side and I kind of trade it over to rebalance it like this. This is one of the intuitions behind the rebalancing operation. That's one of them, but here's the other interesting detail I want to make sure you're aware of. Is if I list it out in an in-order traversal, this binary search tree, on the left, I have T1, so everything that's in T1 would be right here. Then I would have X. Remember, when I do an in-order traversal, I go left all the way, and then I visit myself, and then I go to my right, right? And then I work my way back up. So I have so I go T1, X, T2, then I go to Y, and then I go right, T3. So this is the in-order traversal of the left tree. Or at least what I've inspected as this subtree. Because keep in mind, there could be more up here. That's the one thing that often in implementation details, some students have a trouble remembering that there could be more up here. It's a very common mistake to forget about that. There could be more there. But now let's do an in-order traversal of this one on the right. So we go left first, so I have T1, then I visit myself, then I go right. Then I go left, I visit myself, and then I go right. Notice that they have the exact same ordering. So this is one key idea of the rotations, that it always maintains the binary search tree property. This is actually one of the main reasons why the AVL tree, you like using these rotations, is that it always guarantees that you're maintaining the binary search tree property. Akin to what I was talking about with an invariant, is that whenever I do a rotation, prior to the rotation, the binary search tree property is satisfied. After the rotation, the binary search tree property is satisfied. So the other thing is that when you take these rotations, you can always combine them to create so-called single rotations and double rotations, which allow you to adjust the heights of the subtrees, which is something that AVL trees do. So keep in mind that the rotate operation is reversible. So for example, if I do what is called a right rotate, that's where I'm going to demote Y and bring up X. I get this tree. If I want to bring it back, I want to reverse this operation, I do a left rotate where I bring down X and I promote Y. So that is, this is the rotate operation. Now, for anybody that's seen an AVL tree before, what's the time complexity of a rotation? Of a single rotation? Yeah, it's just constant. It's constant. So that's one thing I want you to remember, is that these rotations, these all take big O of 1 in the worst case. So each of these takes constant time. Why? Because even though this looks rather dynamic, all I'm doing is making pointer adjustments. That's it. I'm just changing around the pointers when I do this. Does everybody see that? So when I promote X, it isn't that like I'm doing some dynamic process, really, like I'm just visualizing it like this. But really what I'm doing is I'm just changing around some pointers. And there's a constant number of these pointer adjustments. Hence this whole rotate operation takes constant time. So just keep that in mind. It's also a nice feature of the rotations. So that's the first idea we're going to use for the splay trees. The other one is something called a path shortening, or the idea is that if I'm going to access or query a given node that has a record, I would like to make those really, really long search queries, which are really far down the tree. I would like to make those shorter. So this is actually an idea that pops up several times if you go exploring more about data structures. It's actually very often used as a heuristic to speed up some data structures. For example, if you do a search query and you know you're going to keep doing that search over and over again, it doesn't make a whole lot of sense to have that node all the way down here at the bottom of the tree. Instead, maybe you want to bring it up closer to the top or near the root of the tree. So there's several data structures that make use of this idea. So it's sometimes used in heuristic circles to speed up some query operations. Now, So I'm going to take both of these ideas, and you might ask, Dan, what does this have to do with amortized analysis? So I must stress that this is an introduction to splay trees. I could easily talk about this subject for 2 lectures, solid. This is a topic that I could go kind of nosedive right into and just not let us leave for a while. Just to be very clear, I want to make sure you walk out of this with an understanding of a splay tree, how it works, and just some intuition behind where it comes from. So the big thing I really want to talk about is this amortized, like looking at this from an amortized perspective. So because when we think about our invariant idea where I do this and it stays this way each time I do that, this is true for rotations, but what about the height of the tree? That's really often what we're interested in, right? But what about the overall time it takes to do all of my insertions, for example, or all my search queries, or all my removals? Instead, if I view things like that instead, things become a little bit different. And it actually, fundamentally, it's about asking a question that you may have thought about when you thought about maybe self-balancing trees. Because remember, the splay tree isn't a self-balancing tree, it's a self-adjusting tree. It won't necessarily guarantee the tree is going to be balanced. It's lazy. It's just going to lounge back here and it's just going to do some very simple things to the tree every time you touch it. It's just going to kind of sit there lounging back, okay? Just like if I wanted to hang up my coat and go put this over there, now I'm going to go sit over there in a chair. That's what the splay tree's approach to balancing is like. So it comes back to a more fundamental question. Is what does it mean for a tree to be balanced? So there's several different ways you can approach this question. One way is you can think about it as, okay, well, could it relate to the length of one of these paths? That's one way you can think about how balanced the tree is. If I can make these paths as short as possible, but like uniformly spread them as far across the tree as I can, some people may view balancing the tree like that, right? Is trying to make those paths short as I can, but not, so this is analogous to me, analogous to us, the thinking about if I give you a node and I work my way down and I look at the depth of a node. So what happens is you can think of it like I have a node in my tree. Say like a node like this one. If suppose I was at this node and I have to go all the way down here. Now, from the perspective of this node, there's some of these have a really long path. In fact, if I were to start right up here at the root, notice that this path is rather long, but there's also a lot of children, like a lot of descendants that I'm going to potentially have to examine their children for records, but I'm going to have to go down one of these pathways, right? So the intuition behind this is that when I have really, really deep nodes, meaning that I have a node here that has a very long pathway, this maintains a lot of potential. So it means that the potential of these is very large. And I would like to reduce these by bringing up those that are really, really down here and bring them up to reduce or alleviate that potential. So you might ask, Dan, how does the amortized analysis play out with the splay tree? There's the 2 common ways I mentioned previously. Like I mentioned 2 other methods, the bankers or accounting method and the potential method. This analysis, if you ever find yourself digging around for it, it uses one of those 2 methods. Potential method is usually the one that people like to go to. Because what you do is you measure these path lengths in relation to what happens over the entire data structure, in relation to insertions, removals, and so on. So the idea is that by rebalancing the tree, I could try to shorten these paths if I use what are called double rotations, which are a kind of rotation. It's actually a combination of 2 of them, hence its name. I can use these to improve the height of the tree. This is actually a property that is actually used in AVL trees. Likewise, if I could try to shorten the paths, I could try to bring these very long paths that lead to high potential on these really long path nodes. If I can bring these up, I can alleviate that. And over time, the overall cost of all of these operations may work in our favor. Because remember, the idea with amortized analysis is that it's a sequence of operations as opposed to just a single operation, right? When we think about AVL trees, we think of just one operation that happens. And then we ask what its complexity is. what we're going to think about is, imagine I had to build one of these splay trees, what would be the time complexity of building the tree if I do a whole bunch of insertions or some removals in there, or I do some searches? We're going to see something rather surprising that comes out of this. So hopefully I've hyped everybody up about these splay trees. Is this kind of neat? So I'm going to kind of bring together a couple of ideas you may have seen in your past studies. But I'm going to do it in a way that's really lazy. I'm going to be lazy about it. And the black magic in this is the amortized complexity that comes out of this thing. So anyways, let's head on over this way. I just gotta, my camera has decided to say, hey, look, I'm just gonna kind of stay right here. There we go. Let's head over here. So at the heart of the splay tree is the splay operation. Now there's several different ways you can cast the splay operation. I'm going to describe it this way. Why? Because it's very easy for me to describe it in terms of rotations. And I want to improve these, I want to shorten paths, so I'm going to try to make the height more balanced. So you might ask, okay, so what's a splay operation then? Because this is at the heart of the splay tree, is if you can have a splay operation, you just modify every single operation of your binary search tree. I'm not even talking about an AVL tree or anything. If you have one of these splay operations, I'll just tell you how you apply the splay operation to the tree. All you have to do is implement this one operation and you can have a splay tree. So you can take any binary search tree that you like. So take your most naive one that has a degenerate structure to it. You add this operation, and I'll tell you where you put them in. As long as you can implement this, you can have a splay tree, and it has some really nice properties. So that's the big thing I really want you to get across here, is that at first it's going to look like I'm doing something that might remind you something about an AVL tree. But it's quite similar, but it's not exactly the same. I'll point out the parallels between the two in a moment. So here's the idea of the splay operation. So suppose, let me just use some of the space I have over here. Actually, no. Let me just explain it with my hands, just for now, because we're going to see an example of this in its entirety. So imagine I'm at a node X. So I'm at some node X, and the root's way up here. What I would like to do is I would like to get this X all the way up to the top by shortening its path. Because remember, I talked about path shortening. If I were to access X again, it would be at the root. And by doing this, I'm alleviating potential in the system. If the system in our case is our data structure. So the whole idea is I'm going to bring X up here, but I can't just grab it and just throw it up here. I can't just throw it like a baseball at the root and knock it out. Kind of like what we did with our heaps. I can't just grab it and just say, yeah, you're out of here. I'm going to just do some stuff to this data structure. You can't do that with this. There's one major problem with it, and it comes back to the binary search tree property. Because I need to make sure that gets maintained at all stages, because it still has to be a binary search tree. Even if I call it a splay tree, it's a binary search tree. So does everybody understand that? So I'm going to have to do something to get X down here, one descendant of the root, and I need to bring it up to the root somehow. But I have a lovely operation that's capable of this. It is, of course, the rotation. Now, I can take this rotate operation that I have over here, I can combine it to make so-called double rotations. You may have seen double rotations before if you've seen an AVL tree. So the first rotation, the first double rotation is not like the AVL trees. The second one is exactly one of the double rotations from an AVL tree. So each of these has a fun name. And I'm not even kidding, I didn't make up these names, just to be very clear. They are actually the technical terms for this, just to be very, very clear. I'm not even kidding, I'm not even messing with you or anything. These are actually the names for these. And it makes it easier to remember what the operation should look like. So the first one is called the zig-zig. Now, just to remind you of how these operations work, is that you're going to start at X down here. You're going to check its parent. And if it has a grandparent, you're going to check the grandparent and see which side it's sitting on. Is it the left or the right? you do something quite similar with an AVL tree, where you examine the parent and then the grandparent, if the grandparent exists. Because obviously if the parent doesn't exist, then you're at the root, right? So you want to think about the zig as if I'm just going to check my immediate parent. So a zig-zig would just simply be two in the exact same direction. So what zig-zig means is, okay, so imagine I'm here. I'm going to go up and up, both in the exact same direction. Keep in mind there's a symmetric case where you go up left twice, where it would be X, Y, Z like this. So you might ask, okay, so what's a zig-zig operation? Well, it's a double rotation. And what we're going to do is, remember, I'm going to keep applying these double rotations until X is at the root. And what will happen at the end of this process is X will be at the root, everything will be, so every other node will be to the left of it, every other node will be either is going to be on the left or the right. Hence why we call it the splay operation. It's like I take open, say if I have a big branch, I peel it down the middle and I put what I want there, and everything else I can spread out like this. Like I'm sitting in my lounge chair. So anyways, let's talk about the zig-zag first. So this would be the scenario that we have. So this is the X I'm currently looking at. I would examine my grandparent and then, my parent, and then if I had a grandparent, I would examine that. There's a third case that I haven't yet given you where you don't have the grandparent. So zig-zag. What this is you apply the rotate operation I just gave over there. You apply it at Y first, which what this does is it promotes Y and then demotes Z. And then what we do is we apply rotate X, which will promote X over Y, bringing X above Y, and you end up with it where it flips it like this. So that's the zig-zag operation. So question, based on our discussion previously, so what's the time complexity of performing a zig-zag? Can somebody tell me in terms of big O? Yeah, it's still constant time. So remember, the zig-zag operation is two rotations. So we call this a double rotation, and there's two of them. Each one of these takes constant time. There's a constant number of rotations happening in the zig-zag operation, so the whole thing takes constant time. This is true for all the rotations I'm going to show you. So this is a nice feature of rotation operations, and it preserves the binary search tree property. But here's the neat thing. Like I mentioned, the potential from our standpoint will get alleviated because I'm going to make the tree more balanced by doing a double rotation. This is sort of an underlying theory that comes from the AVL trees, is that single rotations are used for fixing things up. Double rotations will correct imbalances. So this is sort of my lounge chair approach. I'm going to use a zig-zag. The other case is a zigzag. It gets its name because notice it goes zigzag like this. It sounds like you're saying it out loud, right? You go one direction, then the other direction. So if I have X here, notice that my parent is on the left, and then it flips directions to the right for its grandparent, if it exists. So in this case, the grandparent exists. And keep in mind, the symmetric case would be where it would be X, then its parent is on the right, then its grandparent is on the left. So I must stress that these operations, you don't necessarily have to view it just like a rotate operation. You could literally do all these pointer adjustments if you really wanted to. Some people implement it like that. Some people will actually make a function called rotate, and they'll apply rotate twice. And literally, their code will look like this, where it's just rotate X, and they just do some check just to make sure that the tree isn't empty or something. So zigzag. This is actually exactly the same as another case that actually occurs in the AVL tree. In the AVL tree, this is actually called this is the case of an LR rotation or an RL rotation. It just is called zigzag in the context of a splay tree. So if you've seen AVL trees before, this is the exact same double rotation that occurs there in the AVL tree. So what do you do here? You rotate X, so you promote X, you demote Y. So now Y is coming down, X is coming up. I'm going to trade over T1 over to T0. And then I do another rotate, which I'm going to promote X over Z. And then what happens at the end of this process? X becomes now the parent of Y and Z, and everything will still remain, like I said, in the binary search tree order that we expect. And again, remember, this takes constant time. So are there any questions about these rotations? So these are kind of like, I would argue that the zig-zig is probably the trickiest of the two rotations, because one, if you've never seen these before, the AVL tree doesn't have this rotation. So keep in mind, this isn't the exact same one from the AVL tree. This one, however, is. This is an RL rotation or LR rotation. So this isn't an LL rotation or an RR rotation, if you've heard of these things from AVL tree. Some people even call them similar terms. So, where is zigzag? Oh, zagzag. So here's the thing. Some people like to refer to zigzag as like one direction in the tree, and then they'll call zagzag the other direction. So when zigzag happens, it's just simply one direction, then the other direction. So zagzag is the same as zigzag. However, I did not talk about zig. That's the third case. So let's head over here. I'm going to talk about zig. And believe it or not, zig is like the easiest one. So zig occurs when we don't have a grandparent for X. And the great thing is I already have the picture of zig right here. It's right here. This is actually zig right here. Boom, right? So let me just gonna stop it there. I'm going to reuse things because it saves me a little bit of fun here. So I'm just gonna erase this part in the middle. Okay. So remember, this is X, our X. And remember, there is a symmetric case to this where X is on the right instead of on the left. So if I apply, so the third case is zig. It's quite simple. There's no grandparent. So this happens when there's no grandparent. So this is what happens when you don't have a grandparent. So you're just going to apply zig. And what's zig? So zig is just rotate X. That's it. So isn't that one nice and easy? It's pretty cute. So you might ask, Dan, what does it look like when I actually use these things? What's a splay operation actually look like? So let me show you an example of us using these rotations to splay a tree at a given node. Now I must stress that this algorithm will work regardless of which node I pick in the tree. So the idea will be, once I show you how the splay works, all I have to do is tell you what node to apply splay to, okay? So just remember that. So it isn't that I'm going to go work my way down the tree and then I'm going to pick a node, then I'm going to splay it. Some operations I will do this, some I won't. So as long as you understand how the splay process works, everything you know about binary search trees applies. Everything. So that's a wonderful feature of a splay tree. Like I said, all I'm doing is I'm going to augment a binary search tree. I'm just going to add this splay operation and I'm going to like superpower it to try to make it be a little bit more balanced, but not necessarily perfectly balanced. So let's do an example, because I think it's important you see how you can use these rotations. I must stress that I have two examples. One's going to be, I'm going to do here with you now, and there's another example that's going to be in the notes, okay? So we're going to walk through an example here. By any chance, actually, I'm going to keep zig over there, because it's just a rotate. Let's do an example, because it's important that you get to see this at least once. So suppose I have the following binary search tree. So the root is going to have a key 10. The left child is going to be 7, 12. I'm going to have 3, 9. The right child of 12 is 14. The left child of 14 is a 13. And the right child of 14 is a 16. Now, I'm just going to put in my my leaf nodes just because it makes things a little easier for me to talk about the rotations. Like I said, you don't have to have them at all. You could just replace these with checks, checks for null pointer. But just be careful when you do it. That's the big takeaway here. But I must stress, this is a rather helpful way of dealing with the rotations. You can always optimize it further by getting rid of these. So I'm going to splay. So in my example, I'm going to apply the splay operation. So I'm going to splay at 13. So I'm going to splay at the node that has the key 13 in it. So that's what X is. So just to be clear, X is 13 here. That's whatever the node is. So what I'm going to do now is I'm going to apply each case, and each case is going to get me one step potentially closer to that root. And I stop this when X becomes the root. So watch this. So let's do this. So I have X, I check its parent is to the right, and Y's parent is to the left. So that would be Z. So can somebody tell me, what kind of rotation should I do? So notice I have a grandparent. Which way should I go? So what kind of rotation should I use here? So there's three possibilities, right? We know right away it's not zig. But it could be either zig-zig or zigzag. Yeah, it's going to be zigzag. Notice the easy way to remember it? Zigzag. It's one direction, then the other direction. So what I'm going to do now is I'm going to apply a rotate on Y. So I'm going to bring down 14. I'm going to bring up 13. Now notice that these anchors make this easier to determine which subtrees go where. This is one feature of this type of implementation. So what I'm going to do is I'm going to promote X, I'm going to demote Y, and then I'm going to rotate on X that will promote X and demote Z. And when I do this, I'm going to get, so just keep that in the back of your mind there. So what will happen is I'm going to have 13 here. Remember, that's X. And I'm going to have 12 here. I'm going to have 14 here. And remember I had 16. Remember, 16 got demoted quite early on. So 16 is way over here. So right now, that's where X is. Now, so you might say, okay, Dan, what do we do next? So I have a parent, but I don't have a grandparent. So what case should I apply? Which one? There's only one where there's no grandparent. It's zig. So I'm going to apply zig. So let's apply zig all together. So I'm going to apply zig. That means I'm going to promote 13. I'm going to demote 10. And then I'm going to have to hand over one of my subtrees over to the other side. So just to make this easier for you to see, I'm just going to draw it below here. So I'm going to apply zig here. I knew because I was going to run out of space. That's why I drew it again here. So we know 13 is going to be the root because that's what's going to get promoted. 10 is going to come down to the left. So 10. 14. I'm going to have a leaf node on the left of 14. I'm going to have 16 right here on the right of 14. Then those are going to have leaves like this. Then I'm going to have 12 to the right. Remember, I hand it over. I give it over to my friend over here. Then I have 7, 3, 9, and I have all my leaf nodes down here. I have all my leaf nodes. Now remember, 13 is X. Am I done? Do I have to do anything else? Anything else at all? Am I done? Somebody please tell me, am I done? So I could at least lounge back. I could just say, I'm all done. Remember, the Splay Tree just does this. It was like, okay, that's good enough. I'm gonna go sit over there. Are we done? Is there anything else I have to do with the splay operation? I don't have to do anything else. The splay is finished. Because remember, the goal is to move x to the root. So I use rotations to achieve this. So I have those three cases. I just keep applying them until x is at the root. But now notice, this is why I said it's the splay operation. Notice everything is either going to be on the left subtree or on the right subtree. I pulled up x through the tree. I've kind of like pulled it out, kind of like I'm pulling like a cord that's tangled behind a corner of a wall or something. By the way, don't pull them by their wire. Obviously pull it from the plug. But like you pull it up, you're dragging it all the way up to the root, but all the other rest of that wire is all hanging down on one side. So notice I've just spread out everything like this. But now notice x is at the root. So if I were to access this tree and try to find 13, it's right at the root again. So if ever I do this, you'll see that this will make it a little easier for me to get to 13 again. I don't have to go all the way down the tree. Is that cool? So that's the splay operation. Once you understand the splay operation, I just have to tell you how to apply it. And that's everything about a splay tree, believe it or not. So let's talk a little bit about how we use this. So like I said, I have another example. It's going to be in the notes. It's a little bit, I would argue it's slightly more involved. So you get to play around with this. Now, if you ever find yourself in doubt and you're like, okay, did I do it right? Remember, break it down by the rotate operations. Just take one step after the other. And I usually find that helps students quite quickly. If you can't visualize where, oh yeah, it promotes this, demotes that, and then it grabs over this one. That's how the rotate works, but it's very hard sometimes to be like, okay, this is what a double rotation is. So break it into two pieces if you find yourself just like, okay, I don't know how to do a double rotation off the top of my head like that. Just do rotate. Just remember the order you do the rotations and it's a piece of cake. So anyways, let's talk about the operations of the splay tree. So let's do this. So I'm going to augment each of the binary search tree operations with a splay at some node x. So all I'm going to do is I'm going to go through each one of these operations. I'm going to tell you what x is. That's all I have to do. Is that kind of wild? Like, I'm just going to take your binary search tree you learned in 210, and I'm just going to show you, hey, look, you make this one modification to it, amortized analysis does some weird black magic with it, okay? So watch this. So first we're going to talk about get. Remember, this is where I just do my search with a key. So all you do first is you just perform a search as with the binary search tree. So you just perform the search. So you start off by doing that. There's two possibilities that can happen. So either the search is successful or it fails. Now I must stress that, remember, the way I'm representing the binary search trees is actually a feature. It helps you design the algorithm a little easier. But it comes with a little bit of a penalty because of extra space, but you could easily modify this to just simply check for this case, where you go a little too far off. So, like I said, this is like binary search trees with training wheels. But it has some perks. So anyways, if I were, for example, to get, say I want to get 14, do I go left or right from the root? If I want to get 14. Which way do I go from the root when I search? I go right, and then I'm going to go right again, and then I find 14, right? And then I'm done. However, notice that in the way I represent the binary search tree, if I fail to find what I'm looking for, what happens is I go, like say for example, I'm looking for 17. Now 17 is not in this tree at all, like this one up here. So I could go right, and keep in mind 17 should be over here on the right. But what happens is I end up at a leaf node that has no data in it. So that's how I know I failed the search. Now if you didn't have these leaf nodes here, you'd just be hitting null, right? So that's what I mean, is that there's several ways I could describe the same thing to you. Just this is like one way you could represent it. So now notice that if I fail to find the search, then I could tell you what the parent of this leaf node is. So I'm just going to phrase this in that context. So first, if the search succeeds, X is the node with K. So that's the one you're looking for, right? So you use that as X. So for example, when I did a successful search, I would splay at 14. That's where I would start at. If it fails, otherwise, X is the parent of the leaf node the search reaches. So what I would do if I was searching for 17 and I failed, I would be right here. This is where I would be. I would say, make this X. Do you see how you could figure out what X is when the search fails? And the other way of representing the binary search tree, it would just be the one that you stopped at before you hit null, right? So notice that that's another way you could describe the same thing. So that's all you do with get. That's all you do to modify your search. It's really, really neat. And now, if I do an insertion through the put operation, so I'm going to create a record with key K and value V, or data. So I must stress that I'm going to describe this in the context of a dictionary. Now, dictionaries do have unique keys in them. So there's a possibility I could run into, if I attempt to put a duplicate key in, it causes a problem. So just be aware of that. If you allow duplicates in your tree, you could basically ignore my warning, okay? So perform insert as with a binary search tree. And if K is not found, new internal node X is created along with 2 leaves. Then you just splay X. So just to remind you of how the insertion works in a binary search tree, at least in this representation, what you do is you first do a search. You just search for a record with key K. So you just do the search. So for example, if I want to insert a record with 17 in it, I would go all the way down, I would hit this leaf node. Now, if it's not found, I'm going to create a new internal node right here, call it 17, and I create 2 leaf nodes for it. This would be what X is, the node that contains that record. So just remember, when you do insertions, you search first, and then you just plop it in the spot where it's appropriate. So that's how put works. It's really, really straightforward. Now, the tricky case I need to point out is the remove case. Is it okay by any odd chance I move over there? Because I need a little bit more space, just a little bit more. Okay, so let's head over there. Okay, so now let's talk about the remove case. So if I want to now remove a record with key K, it's a little squeaky. So suppose I want to remove a record with key K. What you're going to do is you're going to splay the node X that is the parent P of the removed node, with key K. So just to remind you a little bit about removals in a binary search tree, just as a reminder, remember, when you do the removal, there's really like two cases you have to watch out for. So the first one is when you have like one child off on one side or no children, and then you could just simply do the deletion very easily by replacing whatever the descendant is as the node itself, or you just simply have no children, right? That's a very easy case to deal with because you can always just sweep to the right and grab whatever you need. The other case is when I have potentially two children, I don't know what to do with this. So what I do is I recursively go down all the way down one side of the tree. I copy the value that would go there if I deleted it. And then I just simply apply the deletion case for this node that needs to go away at that point. So what I'm saying is you just make X the parent of whatever node got deleted in this process. So that's all it is for remove. So just remember, the big thing here is that splay trees are very simple. So just think of it like I have a binary search tree. Binary search trees are much simpler than AVL trees, right? But all I have to do here is just implement the splay operation. I just shove it into the function wherever I want to use it, right? That's all I have to do to make it a splay tree. So just remember, we don't also have to store any additional information. Did you notice that? I didn't have to store any additional information in any of the nodes, right? It's just a binary search tree. Just I do this one operation every time. It's like wowzers. It's quite amazing. So let's talk about what exactly do we get. So remember, that's a big perk because in an AVL tree, you actually have to store additional information. You have to store, for example, a balance factor or what the height is of that node, whichever is more appropriate. So a lot of these self-balancing trees do this, where you have to store additional information. Splay trees, none of that. I'm lazy, okay? Somebody clip that out after. But anyways, so let's talk about the complexity of our operations for the splay tree. So the first thing you should notice is that everything I did here depends entirely on the height of the tree. Just like I had with binary search trees, right? Because every one of my rotations takes constant time, and that's what the splay tree is comprised of, but I could potentially, in the worst case, start at the bottom, at the bottommost level of the tree and work my way up, right? So a splay operation takes big O of H time as it may splay from the deepest, deepest node in the tree. But keep in mind that the height can be, in the worst case, big O of n in a binary search tree, right? So we know that in the worst case, we're going to be dealing with linear time, which shouldn't be very surprising to anybody that's studied binary search trees before. So height h can be big O of n. So all our BST operations, by the way, remember, all of these take big O of h. Take big O of n in the worst case. Now, do you remember the story I was telling you when we first started talking about amortized analysis? Do you remember what I said? to kind of tie everything together. I told you worst case analysis can be very pessimistic. Do you remember I said that? Now watch this. This is going to be the black magic of this data structure. So I'm going to write a theorem over here, and you're going to see why this gets a little bit weird. And this is why I usually like to show this one before we get kind of like to the next part of like our data structures kind of discussion. Is that this is kind of like this is a little wild if you've never seen this before. So in your head, you know, okay, so if I do a single operation, you know, at the worst, it's going to take linear time, right? But remember, if I'm doing a whole bunch of operations on this splay tree, maybe, just maybe, there might be a sequence of operations for which, when I do the whole sequence, all those operations in total, it actually might be much better. So watch this. So I'm going to say the splay trees appealing feature is its amortized complexity. And this is true for all the operations, by the way. It isn't just insertions, it's not just removals, it's all of them. So it doesn't matter which sequence of these operations you perform, this is going to be true. So watch this carefully. So this is going to be a little bit of a wordy theorem, but depending on how much time we have about 5 minutes here. I'm hoping I could write this and just explain a couple consequences, then we'll wrap things up here. So here's the, this is kind of like the killer theorem of this splay tree. And there's a lot of theory, by the way, in data structures surrounding some of the things that involve this theorem. For example, what you could do to modify parts of the splay tree to do certain things that I can't really talk about due to the time constraints of this course. Like I could easily talk about so-called things such as the access theorem and all these other they're very fascinating, but for the purposes of this course, it's a little bit above this, what our discussion is. Because like I said, we don't have like a week to talk about splay trees. So consider a sequence of m operations. So m is going to be the number of operations. Just keep that in mind. Of m operations on a splay tree consisting of get, put, and remove. And I must stress that these are all with the splay operation. Just to be clear, this isn't just a binary search tree. This is a splay tree that we're talking about. Something a little bit more specialized. Just a little bit. Starting from a splay tree with no records. Starting from a splay tree T with no records. So this is the scenario with no records. So here's the scenario. I give you a sequence of m operations. I'm going to start off with an empty splay tree, okay? So I'm going to perform a bunch of these operations. Any sequence of operations that get, put, and remove. So just like what you're thinking about maybe on the assignment, for example, there's some sequence that's going to maximize the cost of these things. And these are determined, at least for the analysis of this, either through the banker or accounting method or the potential method. Usually it's the potential method, if you ever want to go digging into this kind of stuff. So let ni, so ni, like this, be the number of records. Be the number of records in T after operation I and n. So n is going to be, so this is just n, not ni. N be the number of put operations. So there's going to be some, there might be some subset of put operations. I'm calling that n. then the total running time, so remember, I'm looking over this whole sequence, the total running time over all operations is the following. No, watch this, watch this. So it's going to be big O of m plus the sum from I is equal to 1 to m of log base 2 of ni. Like this. But this is, so I'm going to say which is big O of m log n. Which means, so just to be clear, the amortized complexity. So remember our definition of the amortized complexity. So if the total cost is m log n, and I have m operations, the amortized complexity is actually log n. It's big O of log n. Boom. So on average, your worst case, you're going to end up with logarithmic running times, just like the AVL tree. But here's the other cool thing. When you build the data structure, if you think back to, say, something like an AVL tree, when you perform a sequence of operations to insert, say, n elements into, like, say, I'll give it a different name because I have n here. Suppose I use some number of operations to build a data structure that contains that number of records. Notice that that would take, with an AVL tree, n log n time if n was, say, the number of put operations like I have here, right there. So notice that that is the same time complexity you'd have with an AVL tree. So that means that with a splay tree, you can get that same overall time complexity using these very lazy approaches with the splay tree. This is why we call it the black magic of data structures. So with that being said, when we come back next time, so next lecture is going to be a short pre-recorded lecture that you can watch anytime on Tuesday or Wednesday. And we'll come back on the Thursday for a lecture. When I come back in that recorded video, I'm going to start talking about graphs, which is a pretty exciting part of the course. So this is just another chapter in our data structures ventures, but it has a very strong algorithmic edge to it. So I'll say thank you very much and have yourself a beautiful day. I'll see you later.